Welcome to video 3 for our lecture series on Wednesday, March 22nd, where we are going to discuss solubility rules and how that will allow us to predict whether or not a precipitate is formed in an aqueous double displacement reaction. So in order to understand the solubility rules, rather than just memorize them or use a reference table, which we will eventually do, but to start, I think it's a good idea to remind ourselves about why it is a particular ionic solid or solute would even dissolve in solution in the first place. So recall from our electrolyte lab, we discussed that ionic compounds will only dissolve into solution if and only if their ions are more stable in that sphere of hydration, or more stable in solution, than they are in their solid crystal lattice structure. So we looked at sodium chloride as an example. Let's see if I can't find that image here. So over here on the right, we can see the sphere of hydration. That surrounds each of our ions. And the only reason why sodium chloride can dissolve in the first place is because the electrostatic interaction, or the ionic bond that is keeping all of these sodium and chlorine ions together in the solid, or what we might call their lattice energy, is less stable or higher in value than our hydration energy, meaning that the interaction between our ions with the dipoles of water, which creates these spheres of hydration, is a more stable state for each of these ions to exist in, rather than to have them so closely packed together in this crystal lattice or crystal ionic solid structure. And the general rule of thumb is that ions of roughly the same size form very stable crystal lattices. Meaning it is harder to dissolve these more stable solids than it is ones that might be less stable in their solid form, like sodium chloride. So let's remind ourselves about the periodic trend of radius, atomic radius. Here we're looking at ionic radius. So if we look at sodium and chlorine, so I have sodium here in, oh, this is not ionic radius, this is atomic radius. Oh well. If we notice my relative differences in sodium and chlorine, we can see that their overall radii are relatively different. Because of this difference in size, this is why the sodium chloride crystal solid will dissolve in water, because that lattice, or that coupling of ions in the solid structure, is not quite as stable as those ions would be when they are hydrated here. So it's always kind of good to keep this in your back pocket, this idea of ionic radius. So you just got to remember that anytime you add electrons, you're increasing your radius, and anytime you remove electrons from an outer orbital using your PSDF, order for removal. You need to just be mindful of what kind of relative size of these ions are, knowing that polyatomic ions themselves are pretty large. Now, the solubility rules are a list of rules that kind of take all of the experimentally or empirically observed solubilities of different ions and list them in a table. And here they are as a general set. So first up, if we were looking at nitrate compounds, all nitrates are soluble. So nitrates are universally soluble. Meaning that no cation can couple with this nitrate polyatomic anion to create some insoluble product or some precipitate. Our next rule, acetates, another really large polyatomic ion. All acetates are soluble, however, there is one exception. The silver cation, which is one of our D block metals, so it's relatively large. Is soluble. And then up next we have our halogens, so chloride, bromide, and iodide. These are all soluble with a few exceptions. So halogens are soluble, except with some particular transition metals or polyatomic ions. So we've got, again, our silver cation, the lead-2 ion is also one that will form an insoluble product with our halogen ions. And then also the mercury 1 ion. It's one of our polyatomic cations. Those will couple with chlorine, bromine, and iodine to form insoluble products. So these are the exceptions. So chlorides, bromides, and iodides are soluble. Acetates are soluble with one exception. And then all nitrates are soluble. Okay, up next, sulfates, another large polyatomic ion. So sulfates are soluble. However, there are some exceptions. There are sufficiently large cations that will couple with the sulfate polyatomic anion to create stable lattice structures. So sulfates are soluble, except with particularly our heavy group 2 metals and then also lead-2. So we've got our divalent, meaning 2 valence electrons, cations, Ba2 plus, Pb2 plus, calcium 2 plus, and strontium 2 plus. So again, these heavier or larger group 2 cations, and then also our transition metal lead-2. All right, up next we have carbonates and phosphates. Phosphates and carbonates are insoluble, except those of these particular cations, including acid phosphates. So these are insoluble, except with some H pluses and our other universally soluble cations, which are our group 1A cations and the ammonium ion. Then we have the hydroxides. Hydroxides are insoluble, again, with the exception of our universally soluble cations. So same as above with carbonates, phosphates, and hydroxides. The only thing to note is that barium hydroxide and calcium hydroxide are slightly soluble, meaning they teeter on that edge of having a stable lattice structure, but also a stable hydration energy. And then we have sulfides are insoluble. And we have our exceptions, of course, with our universally soluble cations. But then there are also some other exceptions to note. And then we also have our alkaline, earth metals, or our group 2. And then we have, lastly, the universally soluble ions. There are very few exceptions to this, which is why I call them universal. So anytime we're looking at our sodium cation, our potassium cation, and our ammonium cation, these are almost always in compounds that are soluble. So the solubility rules will be provided for you on any kind of assessment. You will need to reference them quite a bit when you're doing your upcoming homework assignments and also when you're looking at your post-lab for the 9-solution problem. And we are going to use these solubility rules to practice in our next video predicting whether or not a precipitate will form as a result of the mixing of 2 solutions of ions. So we're going to look at our double displacement of ionic compounds and see if when our double displaced ions are paired, if they form some kind of insoluble product or a soluble product based on the solubility rules given below. So that is coming up next in our last video, predicting precipitate formation, video 4.